Hi students, I want to discuss a little bit about the electric field, you know. We already know the Coulomb's law. So we know that when we have two charges, right, we're going to have forces between those charges, electric forces between those charges. If the charge have same signs, we know that the forces are going to repel each other, right? So we have two positive charges. The force between those charges is a force of repulsion. We have, for example, here two negative charges, right? Uh-huh. And then in this case, again, we have forces of repulsion, okay? And then if we have uh, charge with different signs, so one positive charge and one negative charge, right? Then we're going to have a force that is a force of attraction between those charges, right? No matter what is the sign, right? Let me say that this charge is Q1, Q1, Q1. This one is Q2, Q2, and Q2. So no matter what is the sign of the charge, we can find the electric force or the force of Coulomb equals to K times Q1 times Q2 over R squared, where Q1 and Q2 are the magnitude of the charges and R is the distance between the charges, right? And K is the Coulomb constant, and we know that K is equals to 8.99 times 10 to the 9, or 9 times 10 to the 9 newtons meter squared over Coulomb squared. So we know this about the Coulomb force. This is the Coulomb's law, right? Well, what we want to introduce now, what we want to introduce now is the concept of electric field. So when we have, a charge, there is a field around this charge. If the charge is a positive charge, like this one, this is my charge Q1 and it's positive, then the electric field uh, is leaving the charge. So we have here, we are representing now in red, the electric field lines. Electric field is a vector, and in this case, these electric field lines, are radial. So this is E. E is the letter that we use to represent the electric field. So when the charge is positive, the electric field lines uh, are radial, and are leaving the charge. In the other hand, when we have a negative charge, right, uh, like this one, the electric field lines are going to be pointing toward the center. So it's going to be like this. Right? So this would be the electric field near to this negative charge Q2, right? It's a vector. Okay, now if we want to find the magnitude of this electric field, we know that the magnitude of the electric field is equals to uh, the quotient between the force and the charge Q. So we can say that the electric field is equals to Kq over R squared. So this is the formula to calculate the electric field at a distance r from a point charge, right? So what it means, I want to give you one example. Suppose now that I have, let me erase. Suppose now that I have one charge Q of 3 nanocoulombs, So suppose that I have a charge Q here, positive. Q is equals to 3 nanocoulombs, right? And then I want to find, okay, the electric field at a distance of 1 meter from this charge. So I will just have a point that I will call point A. And I'm going to say that point A here is just 1 meter from the charge Q, right? Q1, we can say this charge is Q1, right? So I want to find the electric field at this point. You know, the intensity of the electric field at this point that is 1 meter from the charge. So I can say that the electric field will be equals to K times Q over R squared. So it's substituting 9 times 10 to the 9 Newton meter squared over Coulomb squared times what is Q? 3 nanocoulombs. By 3 nanocoulombs is the same that 3 times 10 to a negative 9 coulombs divided by 1 meter squared, right? So of course, we are going now to simplify 10 to a 9 and 10 to a negative 9 will be equal to 0. Sorry, it's going to be equal to 1 because 10 to a 9 times 10 to a negative 9 is 10 to a 9 plus minus 9, so it's 10 to the 0, so it's 1. So we multiply 3 times 9 here, that is 27. Okay. This Coulomb square are cancelled out, you know, with one of the columns of the Coulomb square is cancelled out here with this Coulomb we have of coming from Q1. The 1 meter that I have here below, when I square that, is 1 meter square. That is going to be cancelled, you know, with the meter that I have over here as part of the units of K. So I will get now 27 newtons per coulomb. So what is going to be the intensity of the electric field in this case? The intensity of the electric field will be 27 newtons per coulomb. You know, at 1 meter from a charge Q1 that have 3 nanocoulombs. Remember that the prefix nano means 10 to a negative 9, right? So you have 9 times 10 to a 9 times 3 times 10 to a negative 9. And then we're dividing just by 1 meter. Now, what happens, you know, we can now analyze the interaction between two point charges, right? So suppose that we have 2 point charges that are just close enough, right? So we're going to analyze the interaction between those charges such that, you know, we're going to see how is the shape of the electric field. So we have here a positive charge and we have a negative charge, right? When we have a positive charge and a negative charge, we're going to see how the electric field lines, you know, are going to be like this, right? And this is what is called I mean, we have that the electric field lines are leaving the positive charge and enter into the negative charge, right? So this is my electric field. Well, this is what is called an electric dipole. So this is an electric dipole. Now, if we have charges with the same sign, like for example 2 positive charges, then the shape of the electric field lines will be like this. because remember there is a repulsion. There is a repulsion here, so uh, this is the shape of the electric field lines. When you have charge with the same sign, this is not an electric dipole. You don't have an electric dipole in this case. So electric dipole is when you have different signs, right? There is a principle that is called the superposition principle that can be used, when I want to, for example, using the superposition principle, analyze the action of 2, 3, 4, 5 charges, on the point, on a given point. So there is a way to do this analysis, right? But we're not gonna, complicate this a lot because it's not objective, of our class. So this is what I want to explain, about the electric field. Thank you.